Okay. Another example. This is number 4 from the text. So here we have our vocabulary is just going to contain the starting symbol S and 0 and 1. So now we're dealing with binary values. Our terminal symbols are the 0 and 1, which means the resulting strings we're going to get are basically bit strings. And the productions are just these. S can be replaced by 1-1-S, or S can be replaced by 0. The question is, what is the language generated by G? So if you haven't read the textbook yet, if you haven't looked at this particular example, I encourage you to pause and try to figure that out on your own. Figure out what the language is and see, try to find a nice way to write down what that is. If you've already read the textbook and you recognize this example, then hopefully I'm just clarifying it and not wasting your time. But all right, let's go ahead and figure this out. Let's make a derivation tree. For this, we'll start with the starting symbol S. And one thing we could do is replace S by 0. And then we would be done, because I'm going to drop this down here and say, so I'm going to sort of drop off the bandwagon here and say, 0. We could end our string of productions right there. But alternatively, we can apply the first production and replace the S with 1-1-S. So that would be 1-1-S. All right, we still have an S, right? We could replace that S with a 0, which would end our process. So I could drop off the bandwagon and just have that, 1-1-0. Or I could apply the first production a second time, right? And replace this S part with another 1-1-S. See what's happening here? I could drop out of the process and by putting that 0 at the end, or I could continue the process. 1-1-1-1 followed by 1-1-S. And so on. Drop out, 1-1-1-1-1-1-0, or continue. And I could go on like this forever, so I put a ... This produces a sequence of strings, and these are the elements of the language. So what is that language? It looks like it is a string of 1s followed by a 0, but not just any string of 1s, because whenever we introduce a 1, we introduce 2 simultaneously. 1-1. So that means we are going to have an even number of 1s. So this could be written, you could write this language generated by the grammar as the set of all strings that look like some number of 1-1s. Now, we could write that as the string 1-1 concatenated with itself n times, and then followed by 0. But what could n be? Well, any number, right? You could have none. Like n could be 0, which would give us this first string here. Zero concatenations of 1-1, which is just like lambda, the empty string, followed by a 0. Or it could be 1, or it could be 2 or 3, and so on. So this is where n is any natural number. And there we go. So that's the answer. That is how you can write down the language generated by this grammar. So next, I want you to go through some exercises. I'm going to pose these exercises here and then let you try to figure it out, and I'll put the answers in the next video. So rather than starting with a phrase structure grammar and trying to figure out what the language is, now we're going to start with the language and try to come up with the phrase structure grammar that would generate it. So I've given you 3 languages here. The first is language 1. It is n zeros followed by n ones, where n is any natural number. That means it could be 0 zeros followed by 0 ones. That means we could have like just the empty string, lambda. Or we could have 1 0 followed by 1 1, or 2 zeros followed by 2 ones. Whoops, I miswrote that there, sorry. 2 zeros followed by 2 ones, or 3 zeros followed by 3 ones. But the key is that the number of zeros and the number of ones are equal, right? And so on. So that's the language 1. Language 2 is 2 zeros followed by some number of ones, a string of ones. And that string the n here has to be a positive integer. So in this situation, I am not including the possibility of 0 ones. The very simplest string I could have is 0, 0, 1, because the lowest value of n is 1, being positive integers. But then I could have 2 ones, or 3 ones, or 4 or 5, or however many. So that's our language 2. And then language 3 is just described. It's the set of all bit strings with an even number of 0 bits. So if it has a single 0 in it, that's not in the language. But if it has 2 zeros, it is in the language. If it has 8 zeros, it's in the language. And it doesn't matter where those zeros are. They could be consecutive or not consecutive. We're just counting how many. Remember that 0 itself is an even number, so if you have no zeros in your bit string, that would still be in this language. So there's the 3 languages. See if you can come up with phrase structure grammars that generate those 3, and I'll go through some possible solutions in the next video.